Hey everybody, Dr. A here, and in this video we're going to be providing some background information on flow of water through soil. So let's go ahead and get started. Water flows through the interconnected voids between soil particles, okay? So think about it, whenever we have soil particles, maybe we have some granular soil particles like this, maybe we have some flat, flaky clay particles in the mix as well. Whenever you have the presence of water, it will tend to flow in between these solid particles, okay? Now, the rate in which water flows through soil is quantified by the soil's hydraulic conductivity, which we use the letter K to indicate that. Now, before we get into the details of hydraulic conductivity, what we first need to do is review some important principles from our knowledge of hydraulics and fluid mechanics, okay? So we're going to say from hydraulics, or maybe fluid mechanics, so we can say from hydraulics and fluid mechanics, we recall Bernoulli's equation, okay? Bernoulli's equation. Now, what is Bernoulli's equation from our previous knowledge of hydraulics or fluid mechanics? Well, Bernoulli says that our total head, which we can call H, is computed by the following. Total head is equal to pressure head plus velocity head plus elevation head. So let's make a note here. This right here is pressure head. That's H sub P. H sub V is velocity head. And H sub Z is elevation head. Okay? And if you add those up, that gets you total head. Now, what are each one of these components? How do we evaluate each one of these components? Well, pressure head, H sub P, is equal to what's called pore water pressure, which we use the letter U to signify that, divided by the unit weight of water, okay? Velocity head, H sub V, is equal to velocity squared over 2 times acceleration due to gravity, so 2g. And then elevation head, H sub Z, is just equal to Z, which is an elevation. Okay, so we'll make some notes here. U is called pore water pressure. And of course, gamma sub W is the unit weight of water, so I'm not going to write that down. V is velocity. G is acceleration due to gravity, so that would be like 32.2 feet per second squared or 9.81 meters per second squared. And then Z is just an elevation or a distance, okay? So these are the two that we need to, make sure we remember most notably, okay? Now, when we think about water flowing through soils, the velocity is going to be very small. So let's make a note of that, okay? Water flowing through soil will have a very small velocity, which is V, okay? And because of that, water flowing through soil will be laminar, okay? So we're going to say, make a note here, this is laminar flow, all right? Now, because of that, we can neglect the velocity head, which is H sub V, for flow through soil, all right? Now, when we do that, our Bernoulli's equation simplifies. It becomes total head is just equal to pressure head plus elevation head. And if we want to substitute those terms in from earlier, that's pore water pressure divided by unit weight of water plus an elevation Z. Okay, so let's illustrate this for a soil sample. Okay, so consider the following. Consider the following. All right, let's consider that we have a soil sample, and that soil sample can be oriented at some angle like this. And let's say that we have flow going through this soil sample, just like this. All right, now let's say for a reference point, we have a datum down here. Okay, and let's call our datum elevation 0.00. Okay, so everything is going to be referenced from the datum. Now let's say that we insert two piezometers. Let's say we insert a piezometer here, and we'll call this point A. And let's say we insert another piezometer down here, maybe on the downstream side at point B. Now when we insert these piezometers, we'll make sure we label these. These are piezometers. When we insert these piezometers, the water level will tend to rise in these piezometers, and it'll rise to different levels. Okay, so notice that these water levels are not the same. Okay, now let's go ahead and consider some other elements of this. First, we're going to have a flow length. Okay, draw that a little bit better for you. This right here is going to be L. We're going to say L is the flow length. That's the distance from point A and point B where the piezometers are located. All right. Now, the first measurement we're going to note is this one right here. The physical distance from the datum to point A is going to be the elevation of point A. We can call that Z sub A. All right. And then similarly, we'll have an elevation from the datum to point B that we're going to call Z sub B. So those are our elevation heads at points A and point B. Now, what about the pressure head term? So the pressure head is going to be the distance from point A up to the level of the water in the piezometer, okay? So this will be pore water pressure at A divided by unit weight of water. And then similarly, we're going to have a pressure head at point B. This will be U sub B over the unit weight of water. So again, the pressure head is going to be literally the distance that water rises in the piezometer from the point of interest up to the water level. And we have a pressure head at A and B. So if you want to put some extra labels here, we can say H sub PA, that's the pressure head at A, is equal to UA over gamma water. And then H sub Z A, which is the elevation head, is Z sub A. And similarly, we can say this is the pressure head at point B, and this is the elevation head at point B. Okay? Now, these are how everything is related together. Now, what about this difference in elevation right here, or this difference in head right here? This difference is the change in head. We're going to call that delta H. So delta H is the change in total head from A to B, from point A to point B. So delta H is just going to be the total head at A minus the total head at B. So we can package this together by saying UA over gamma water plus Z sub A minus UB over gamma water plus Z sub B. All right. So literally we're taking this total dimension minus this total dimension. All right. Now, the next property we can extract from this is the hydraulic gradient. Okay. The hydraulic gradient is what we call little I from hydraulics and fluid mechanics. And we say the hydraulic gradient, little I, is equal to that change in head, delta H, over the flow length, L. So again, the hydraulic gradient, it's like a slope almost. It's this delta H here divided by the flow length, L. All right. That is pretty much the summary of how all this pieces together from our knowledge of hydraulics and fluid mechanics. So I want to make a couple more notes. We're going to say, or one more note really, flow in soils occurs from higher head to lower head. All right, so that's our background information to set the stage for our understanding of flow through soils. Be on the lookout for other videos that allow us to go into more detail with these components. Thanks for watching. Please hit like and subscribe.